Power. Power. It is often important to know not only if there is enough energy available to perform a task, but also how much time will be required. Power is then defined as the work that is done, or the energy that is transformed, by work or energy over time. Work is measured in joules, and time is measured in seconds, so the unit of power is joules per second. In honor of James Watt, who made critical contributions to develop efficient steam engines, the unit of power is known as a watt, capital W. On the left-hand side here, we have a 60-watt incandescent light bulb. It converts 60 joules of electrical energy to heat and light energy every second. Getting hard to buy these, okay, because they've been replaced by what? LED bulbs. This is a 9-watt LED bulb. It converts 9 joules of electrical energy to mostly light and very little heat every second, and provides the same light output. Power companies build residences and businesses by how much energy they use. The energy used is found by multiplying the power of the electrical devices times the time it is consumed. The unit is kilowatt hour, and that's a little k, capital W, little h, where kW, a kilowatt, is 1,000 watts. Let's see how much a 9-watt LED bulb will consume if you operate it for 6 hours a day for a 30-day month. We have our 9 watts. It's a 9-watt bulb. That's the power. We convert that to kilowatts here. 1 kilowatt is 1,000 watts. It's ran for 6 hours a day for a period of 30 days. Kind of an exercise in unit conversion here, because let's see what happens. Days cancels out, watts cancels out, and we're left with kilowatt hours over here. So you do the math and you get 1.62 kilowatt hours. The average cost of a kilowatt hour is 15 cents. So the cost of operating that light bulb for a month is just 24 cents. So this was the same as what, a 60-watt incandescent bulb? So that's what, roughly 6 times as much. So that's going to be around $1.25. Now that's not a lot. It's one light bulb, but you have lots of light bulbs, and you have other more powerful electrical equipment that draws more energy. So anything you can save will help. Since power is defined as work over time, and work is equal to FD parallel, we can substitute in FD parallel here, divided by time. We then rearrange that a little bit. We put D parallel over T, and we leave F by itself. Now, what is D over T? It's velocity. So power is also equal to the force times the velocity that's in the same direction. Another useful expression for power can be derived from the work-energy equation. So we have power is work over time, but the work-energy equation, well, that's E0 plus work equals E final, or work equals E final minus E initial. Plug that in for work, and there you go. The power absorbed by a system can be thought of as the rate at which the energy in the system is changing. A heat engine does 23 kilojoules of work during 1800 seconds. Find the power supplied by the engine. We write out our givens, and realizing that 23 kilojoules is 23,000 joules. Then we have our power equation, work over time, substitute in the givens, and we get 13 watts. How much work is done by a 15 kilowatt engine during 3.5 minutes? We start our problem with some conversions. 15 kilowatts is 15,000 watts. 3.5 minutes, 210 seconds. We have our power equation. We solve that for work by multiplying both sides by T, plug in the numbers, and we get the work done is 3.15 times 10 to the 6 joules. How long must a 400-watt electrical engine work in order to produce 300 kilojoules of work? We have our givens, and we convert the kilojoules, right, 300 kilojoules to 300,000 joules. Power equation, solve for time by multiplying both sides by T and dividing by P, and we get work over power. Substitute in our givens, and we get 750 seconds, and we can convert that to 12.5 minutes if you'd like. How much power is required when using a 12 Newton force to push an object at a velocity of 3 meters per second? We write our givens, and this tells us what equation we want to use for power. We need force and velocity. So power is equal to force times velocity, that's the equation. Substitute in the givens, and we get 36 watts.